Hi guys, it's day 9 of the trig unit, and we are finally going to start doing some graphing, which is kind of cool when you see the patterns that happen, or at least I think they're kind of cool. You got to remember, you and I don't always see things the same way. That's okay. All right, so what we are starting with is a quick reminder of the unit circle, because the reason for the unit circle is to be able to evaluate sine and cosine at the quadrantal angles. And those are going to be the points that we plot on the graph so you can kind of see, like, what does this thing look like? Mm-hmm. So what I want you to remember is on the unit circle that for an x, y point, x is the same as the cosine of the angle, y is the same as the sine of the angle. So when we go through all the way around the circle, we're going to be evaluating for sine, evaluating for cosine. It'll be really quick. So I'm just going to label the quadrantal angle values here. So at 0, that's the point 1, 0. At 90 or at pi over 2, that's the point 0, 1. Over here at 180 or pi radians, that's negative 1, 0. Down here at 3 pi over 2 or 270, that would be 0, negative 1. And then, of course, we come all the way back to 0 or 2 pi right here at 1, 0 again. All right. So let's rip through and let's do sine first. So sine is always the y coordinate. So sine of 0 would simply just be the y coordinate here, or 0. At pi over 2, now you're coming up here, it's 1. At pi, it's back to 0. 3 pi over 2, now we're down at negative 1. 2 pi, we are back to 0. All right. To graph this, you have to be able to label the axes appropriately so you can kind of see what's going on here. So something I want to keep in mind, we'll come back and do cosine in a moment. Shift down here. It's saying we're going to use the values along with the unit circle to create the graphs of y equals sine of x, y equals cosine of x. Okay. For sine, the one thing that really is helpful, x is the same as the theta, or the angle. All right. So on the x-axis, we are labeling everything in radians. Right? On the y-axis, that's the ratio that you would typically get out, like the opposite over the hypotenuse part, or in this case, the y-coordinate part. All right. But I'm just going to remind you that that is the ratio there. Okay. So if you look, what x values can I have? Well, I can have any angle I want. We just did 0 to 2 pi, but it keeps going beyond that. You can also have negative angles because that's just a negative rotation. So I'm going to label along here starting at 0 in terms of radians. To spread this out a little bit, I'm going to go every other line. I'm going to let that be a quadrantal angle. So that's pi over 2. Go 2 more. Make that pi. 2 more. Here's 3 pi over 2. And then 2 pi. And that keeps going. This would be, 5 pi over 2 and so on. If I went the other direction, back here would be negative pi over 2 and then negative pi and so on. So that x-axis, it keeps running because the domain is anything from negative infinity to positive infinity, right? The range of values, though, if you take a look back at the unit circle, the y value goes anywhere from 0 up to positive 1, and then comes back to 0 down to negative 1. It never goes beyond 1 or below negative 1. So the range of values that we're going to graph here only fall from negative 1 to 1. It never goes outside of that. And so what we're going to see is the graph's going to kind of bounce back and forth between those two values. So let's plot what we have. What I mean by that, to plot these as actual points. Remember, x is the angle, y is the actual value. So up here, this is the x, that's the y. So we're going to plot that as our first point. So 0, 0. So on your graph, I got 0, 0. Then the next point, here's your x, there's your y. So go to pi over 2 and go up to 1. Now I didn't label my y-axis. I probably should do that. So I'm going to make this 1, and then I'll come down here and make that guy negative 1, just to spread it out a little bit. All right. So at pi over 2, it goes up to 1, and then x, y, so go over to pi, and you're back at 0. X, y, go to 3 pi over 2, and we're down to negative 1. And then 2 pi, that's my x, that's my y, I'm back at 0 again. Now, if we connect the dots, it does sort of look like you have a straight line here. I want you to make it a nice smooth curve. So if you watch mine first, we're going to come up and then down and back up. So it has a nice like flowy curve shape right there. And that shape keeps going. Because if I think about what would happen at 5 pi over 2, 5 pi over 2 is the same as pi over 2. It'd be right back up here at 1. So that would keep on going. If I think about what's negative pi over 2, well, negative pi over 2 would be down here. That would come back to negative 1 and 0. And we would see the graph extend like that. And so it would literally keep going. We say it oscillates back and forth, bouncing back and forth and back and forth. So it's like a pretty little wave, right? So that's what the sine curve looks like. Right? So the domain, everything, negative infinity to positive infinity. But the range, it just bounces back and forth between -1 and +1. So I'm going to say the curve keeps repeating. So every time that angle wraps around the circle, you get that same curve that goes over and over and over again. Right? Now, this part going from 0 to 2 pi, that's called one cycle of the curve. We'll get into that more later. But before it starts to repeat, that's referred to as one cycle. All right, so let's do the exact same stuff for cosine. I'm going to go a little bit faster for cosine. Keep in mind, you can pause the video, you can rewatch it again, but cosine is equivalent to the x value. So at 0, the x value is 1. At pi over 2, it's 0. At pi, it's -1. 3 pi over 2, it's 0. Back to 2 pi, it is at 1. So I want to label the graph the exact same way, and then I'm going to plot all those points. So I'm going to slide down here. I'm going to label my x and y axes with the exact same scaling. And a reminder there that that's, my theta. And then my y, that's my ratio. You're going to notice it's the same values, zeros, ones, negative ones. So you're going to label that y-axis the same way. And now let's plot the points. So for cosine of 0 equaling 1, that is the point 0, 1. So at 0, go up to 1. At pi over 2, we're at 0. At pi, we're at -1. At 3 pi over 2, we're at 0. And at 2 pi, we are back up to 1. So it almost looks like it forms a V, but remind yourself, it's wrapping around that unit circle. So the same curve that a circle has, so does this graph. So it's going to curve here, and then it's going to curve opening kind of up, and then curve back down. And then just like the graph above, this would keep going. This would repeat again, this would repeat again, and so on. So we're just graphing one cycle of it right here. But the domain, it goes on forever. So positive infinity to negative infinity, or oops, other way around. Negative infinity to positive infinity. The range bouncing back and forth from -1 to 1, and it includes those values. So we use the brackets there. So that's the basic shape. So if you're looking at them, you might look at it and be like, it looks like the same wave. Little, I guess, letting the cat out of the bag. It is the same thing. It's just shifted over, all right? But it is the exact same thing. It's just a matter of where does it start? And that's going to be a big thing that we look at, all right? So when we flip it on over, oops, to the next page, it's saying, how can we use the unit circle or the knowledge of the graphs to evaluate sine or cosine? This is just another way to do it. So anytime you're trying to evaluate for a quadrantal angle, remind yourself 270 is the same as 3 pi over 2. So what I could do is I could think about the sine curve. Now that means you're going to have to start to be able to recall what the sine curve and the cosine curve look like. So the sine curve starts at 0, goes up and down, and then comes back to 0 again. So if I sort of sketch that, it goes up and down and comes back. When we do our practice with graphing, I'm going to say that you have to plot like 5 anchor points. What I mean by that, the start, the finish, dead center, there's 3 of them. Hits top, hits bottom, there's the other 2. Those are my 5 anchor points. And each of those anchor points is a quadrantal angle. So here's 0, there's pi over 2, pi, here's 3 pi over 2 right here. So what's the value there? Well, it's -1. So do you have to do it this way? No, You could simply go back to the unit circle and do it that way, but it's just another way to do it. So same idea. If we play the game one more time, cosine is the same as pi over 2, right? The cosine curve, I'll bring my other paper back. Cosine curve starts at 1, finishes at 1, hits -1 dead center, and then halfway between hits 0. So I'm going to sketch that here. Starts at 1, finishes at 1, dead center hits -1, halfway between hits 0, hits 0. All right, there's my cosine curve. So where's 90? Well, it's the first point off of 0 here. So there's my pi over 2. So the height there is 0. All right, that's it. If you are like, I don't love it, then go back to using the unit circle. So unit circle just means that in a case like this, I would say, okay, -5 pi over 2. Well, here's negative pi over 2, negative pi, -3 pi over 2, -2 pi. There's -5 pi over 2. That's the point, 0, -1. And cosine is always the x coordinate. So it's 0, right? You are not forced to use the curve to evaluate, but you do have to know what the curve looks like. Now, can you use your calculator to help you? Heck yeah, you can. All right. So on your calculator, the only thing you want to make sure of is you do need to be in radian mode. All right. Because anything on the calculator, graphing wise, you'd have to kind of change everything over. So just roll with me on this one, switch it to radians. And then when you go up here, ooh, I still had some logs in there. When we go up here, we can type in now sine of x. And then you can always pick zoom trig. That's the best. Oops, let me slide that over there. Zoom trig so that you can see it. And it'll give you a nice window. So now when I hit graph, there's that pretty little sine curve. Right? So the one cycle of it is just that portion right there that goes from 0 up to 1, back to 0 to -1, and then finishes, whoops, back at 0 there. Right? But there you go. When it says, how do the graphs confirm what we know about the quadrants and where they're positive or negative? I don't want to spend a ton of time on that, but if I use the sine curve as my example, so sine curve starts at 0, ends at 2 pi, hits dead center at 0. There's 3 of my anchor points. All right, halfway between each of those. So pi over 2 and 3 pi over 2. It hits top at 1. It hits bottom at -1. Look at that beautiful curve. All right. When it says, how does it confirm where you know they're positive or negative? Well, that goes back to the whole ASTC. We know that the sine curve is positive in quadrants 1 and 2. But what the heck does that mean here? Quadrants 1, 2, 3, and 4 are not the same thing as when I rotate an angle around. It's not the same. But what is the same is any angle in quadrant 1 and 2 when I'm drawing it as a rotation falls between 0 and pi radians. So what we know is that any angle between 0 and pi radians, sine is positive. Well, look at the graph from 0 to pi. It's above the x-axis, meaning those are all positive values. Any angle from pi to 2 pi, down here in quadrants 3 and 4, sine is negative. Well, look back at your graph. From pi to 2 pi, the graph falls beneath the x-axis where all the y values are negative. That's all. That's the comparison. So here it's a rotation. Here it's literally like you're rolling it on out from left to right. All right, let's talk about some vocab because trigonometry has a lot of its own little language to know. So when it says we're going to be looking at the graphs and how to transform it, of course we are. We've done transformations with all the graphs that we've done all year long. Right? So anytime, think back to our transformations unit, unit 2, we have a number sitting in front of the function. Right? That always is a vertical dilation or vertical compression, depending on what the value is itself. Right? We try to avoid it, but if we ever have anything added or subtracted on the inside, that's a horizontal, or sorry, brain fart there. If we have anything multiplied, on the inside, I had to stop myself. I'm like, that doesn't sound right. That's a horizontal dilation. So that's the one where, like, if it's times 2, then it's really x divided by 2. It's the one that's a little quirky. There. And now, if we have something added or subtracted, that shifts it left or right. So that's a translation or a shift going left or right. So you could call that a horizontal shift, right? And then the last thing is if I have something added out on the end, that shifts it up or down. So you can say a vertical translation. Ooh, making up my own spellings here. Or a shift, and this is going to go up or down. Let me remind you, you can pause the video. I know I write kind of speedy. That's okay. All right. In trig, all of those things still stand, but they have a different name associated with them. So it's just some vocabulary that you'll have to get acquainted with. So a vertical dilation, when we talk about trig graphing, is called the amplitude of the graph. Which is kind of nice because if we're talking about like the A out front, A for amplitude, it matches, right? I would love to say that everything else matches perfectly, but not quite. The next one, B, does not start with B. When you have a horizontal dilation, that is actually called the frequency in a trig graph. And that is something we'll talk about a bit. Phase shifts. A phase shift is if you're shifting the graph left or right. This is what we're going to actually be trying to avoid a little bit. We will address it some, but not a lot. All right. The part D, if you shift the graph up or down, what it does is it moves the middle of the graph, or what's called the midline. Sometimes it's referred to as the wrap line because it kind of looks like a sine and cosine curve wrapped back and forth around some like middle line. The way we drew it, the middle line is the x-axis itself, but that line can move. All right, the last thing, I want you to put a couple stars next to the frequency because the frequency is directly related to the period of the graph, right? So the period of the graph, that is the length of one cycle of the graph. So I mentioned on the first page that when we drew just like that up, down, and back, that was called a cycle. The period is literally how long is the cycle. So what we looked at, it went from 0 to 2 pi. So the period would be 2 pi, all right? But the key is that it's directly related to the frequency. So those two are attached. You can't change one without it affecting the other. All right, the very last page. We just want to talk about for the parent functions, what are the amplitude, frequency, phase shift, and midline? So flipping on over to that last page. So for the first one, I'm going to remind you that the equation in that big old fancy form, slide up top here, there we go, is y equals a sine of b times x plus c plus d. All right, here we go. A is the amplitude. Right. So for this parent function, that's what this one is, the most basic sine curve that we could possibly have. The amplitude, if I don't see a number there, is just simply 1. Right. And what we'll come to realize is that affects kind of like how far up and down the graph is going to go. All right, the b value or the frequency, that's the number in front of the x. Again, that's just a 1 right there. So that means that we see one cycle from 0 to 2 pi. Mm-hmm. The phase shift would be if I was adding or subtracting anything to the x on the inside of the parentheses. There's nothing added there. So it's not a 1 because otherwise I'd see a +1. You got to think, what do you add that you don't see? That's a 0. So the phase shift here is 0. Just means I haven't shifted it left or right at all. Easy peasy. That's it. All right, the midline. The midline is any value D that would be added or subtracted afterwards. Well, there's nothing added out here. So if I don't see anything, that is also a 0. And what that 0 actually corresponds to, that's the equation of the midline. It's y equals 0. Because think about the line y equals 0. That is the x-axis itself. That's the line that runs right through the middle of our curve that it's wrapping itself around. All right, last thing, the period of the graph. There's multiple ways to talk about it, but for right now, since the period represents the length of the curve, let's look at that one cycle. Here's one cycle. So it goes from 0 to 2 pi. And so to get the length of one cycle, you can take the point that it ends at and subtract the point that it started at. So if I do 2 pi minus 0, 2 pi itself is the actual length of the curve. So that is the period. All right, that's how much I have to look at to see it. All right, if we answer all those same questions for cosine, you're going to see kind of the same thing going on down here. The only difference is that I would write it as y equals, a cosine of b, and then x plus c, and then plus d. But since this, again, is a parent function, all those values, there's really not much to see. The a in front is 1. The b in front is 1. Oops. That's a. That's b. Let me fix that there. So that's just 1 right there. Right? C and D, those are things that would be added on. So plus C plus D out here, there's nothing. So it's 0 and 0, or again, the line y equals 0. All right, and then the period. Well, if all I see is one cycle from 0 to 2 pi, which is exactly what we've got here, one cosine curve, then the period is 2 pi itself. That's it for day 1. We will do more practice with the basics, getting yourself familiar with how to graph it, how to make sure we plot all 5 anchor points correctly. And then we're going to see what the heck happens when we change the amplitude, change the frequency, and so on. All right, guys, have a great day. Make sure you're getting that homework done.